Good afternoon, everyone. Welcome to our physical science online learning. So, we are on our fourth week for the fourth quarter. See, we're almost done. Our topic for today is all about special theory of relativity. For our learning objectives for today's lesson, first, we have explained the conflict between the theory of electromagnetism and Newtonian mechanics. And for number two, explain how special relativity resolved the conflict between Newtonian mechanics and Maxwell theory of electromagnetic. So these are the things that we are going to discuss all through the given time for us. Okay? Okay, students, try to check this out. I have here few pictures prepared. What you have to do is to tell me what the picture tell us about. Okay, so how about this? Very good. Yes, there is motion. And how about this? Try to look at. So what it tells us? Okay, you are correct. There is distance between the sun and the planet Earth. And we have the last one. Oh, it's an alarm clock. It's a clock. So when there is a clock, it usually tells us the very good. Yes, it tells us the time. Okay? In order to understand physics, so one must start with a thoughtful learning experience of motion, time, and of course, space. So when we say space, this refers to the distance. So since these three are in every activity of our daily living, so one can fully understand our interaction with everything here on earth and even everything outside it. Okay, students, before we will proceed with a brief discussion on conflict of Newtonian mechanics and the theory of electromagnetism and how the special theory of relativity resolved that conflict, let us first answer the drill. Direction. Complete the table of electromagnetic spectrum of light. So write your answer on a piece of paper or on your notebook. Because after that, we are going to check your answer. Okay? So 1 minute to do this. You may now start. Okay. So here it is. So the answer for number one, you have the color red, orange, yellow, then the green is there. Then next is the blue, indigo, and the violet. And for the next, for number six, okay, So we have radio wave, microwave, then the infrared, ultraviolet, X-ray, and the gamma rays, of course. Okay, let me check who got perfect or 9. Okay, so that is good. So thank you. Now, o- okay, to start with, this is showing you the electromagnetic spectrum of light. So this is how the color is being arranged. So you have the red, orange, yellow, green, blue, and the violet. Okay? And also the corresponding wavelength. So the theories. So long before the development of the special theory of relativity, there were two great theories of physics. The theory of electromagnetics developed by James Clerk Maxwell and the three laws of motion by Isaac Newton. So the special theory of relativity was coined and developed by Albert Einstein in 1905 as an answer to the long-debated conflict between James Clerk Maxwell's theory of electromagnetism and Isaac Newton's three laws of motion. So for Newtonian mechanics is grounded in the use of Newton's three laws of motion. So the mechanics explains that space, this refers to the distance, time, and mass are absolute. So this means that the distance between two objects and the time that passes between two events does not depend on the environment where the object is in. Okay? So furthermore, according to Newton's second law of objects in the environment moves in a straight line. Hence, the change of location from one environment to another environment must register a straight line to other straight lines. Moreover, it is said that no matter where you are or how fast you are moving, there will be no changes in space or time. So in all places, a kilometer is always a kilometer, and a minute is a minute, and you can travel as fast as you want with adequate acceleration. So that is for Newtonian mechanics. Now we'll go to Maxwell electromagnetic theory of light. So James Clerk Maxwell had predicted that the electric field, magnetic field, and light are different representations of the same phenomena or event. He further predicted that visible lights are electromagnetic waves that move in a manner like ripples in the water. So when a stone is dropped. So according to Maxwell, light as a wave have both electrical and magnetic components and that it moves at a constant speed of 186 miles per second. It means that the speed of light is the same for everything and for all observers. Okay? So now the conflict is there is there is only one conflict between the two theories. So according to Maxwell, light in a vacuum moves at 186,000 miles per second. and it does not change for all observers and situation. However, according to Newtonian physics, all speeds are relative, meaning the speed depends on the observer's viewpoint and the situation. Okay? So how they resolve Einstein in the special theory of relativity. So in 1905, Albert Einstein published his observation about the differing ideas of the two theories through the special theory of relativity. So his theory is based on the observation of events from different viewpoints. So he stressed that while Newtonian physics is true, Maxwell theory is also correct. He resolved the opposing ideas by establishing the two foundations of the special theory of relativity. So the first principle of Einstein theory is the consistent law principle. It states that all motions are relative to the selected reference frame or viewpoint. It means that the motion of an object is based on the observer's viewpoint. So I hope it is clear. Okay. So the laws of physics are the same in all frames of reference that are moving at a constant velocity with respect to one another. So we have here an example. Okay, a teenage boy is standing inside a train that is passing equally between two oak trees. Because the train is moving, he saw that a lightning struck the tree on his left first, then the tree on the right. So another boy who is standing at a train platform also saw the same event. So only in his viewpoint, the lightning struck both trees at the same time. Okay? So the second principle in Einstein theory deals with the speed of light. So this is the constancy of speed. So he established that light moves in a speed of 186,000 miles per second and is the same for all observers' viewpoint. Okay, now we will move on to the consequences of the postulates of special relativity theory. Okay, so our learning objectives for this lesson is explain the consequences of the postulates of special relativity theory. So the special relativity theory, it was developed by Albert Einstein in 1905. This theory explains how time and space are connected for objects traveling at a uniform velocity. Objects moving and approaching to the speed of light, which is commonly denoted as c and is approximately 3,000 km per second, is one of the aspects that concerns special relativity theory. Okay. So, did you hear about the story, the twin paradox? So if ever you didn't, then please listen. I will read this for you. John and Paul are identical twin brothers. Growing up, they have the same sets of everything. They even have the same clock and ticks at the same time. So John grew up to be an astronaut and Paul grew up to be a scientist. So John became an exceptional astronaut and participated in a space mission that searched for signals of other habitable planets outside the solar system. So John's space shuttle reached the edges of the solar system, which is about 4.3 light years away from Earth in 5 years, and then traveled back to Earth in another 5 years. So flying nonstop at constant velocity. So meanwhile, Paul turned out to be a great physicist back on Earth. After 10 years of in space and about 8.6 light years in distance traveled. So John's shuttle finally landed on Earth. So the twins' parents were shocked to find out that their identical twin is not identical anymore. Paul looked like he aged more when compared to John. To add to their parents' disbelief, John and Paul laughed it off as if they what happened, speculate what happened to their identical twins. So is this scenario possible? Okay. Okay, you have here the key concept of special relativity theory. So later we will discuss this one by one for us to or for you to understand the special theory of relativity. So you have here the time, what is involved, the time dilation, relativity of simultaneity, cosmic speed limit, then mass energy equivalence, and the length contraction. Okay. So special relativity theory is a theory which predicts how events are measured with various observers who are in motion with respect to an event. So an event is just a physical happening. Example, exploding firecrackers, a passing rocket, or a flash of light. So what's so special about this special relativity theory? It is because each observer's reference frame or perspective is a special type of reference frame called inertial reference frame. So this means that the observer is at rest and not accelerating from the observer's perspective. Okay? For example, observer A. So we have here observer A and observer B. So observer A is sitting on a train station. Observer A's position is an inertial reference frame because he or she is at rest or does not move from his or her perspective. Okay. Kasi nakaupo lang siya. While observer B still is sitting on a train approaching the train station with constant velocity. So observer B's position is still an inertial reference frame because although the train is moving, it is not accelerating or not gaining or losing speed. But are they not truly moving? In this case, the answer is yes. It is because in special relativity theory, the effect of gravity, the Earth's rotation, and its revolution around the sun is neglected. Okay, so the special relativity theory has two postulates or assumptions. One is the relativity postulate, where it is assumed that the laws of physics are the same in all inertial reference. And number two, the speed of light postulate, where it is assumed that the speed of light in a vacuum is always the same. So consequences of the postulate of this special relativity theory. Now, relativity of simultaneity. So the relativity of simultaneity is a concept is special relativity theory, which says that if two events are separated in space or position, it is absolutely impossible for the two events to occur simultaneously for the two observers. So two lightning may strike the front and back end of a moving train at the same time from an observer inside the train perspective. But for an observer outside the train, the lightning strike may not occur at the same time. This concept can be illustrated using one of Albert Einstein. Okay, so you have here, there is a lightning, then look onto the arrow where it is going. So both see the light travel where it moves. And for the event 2, what happened? The man is outside the train. So looking at the light. Okay. So we have now the time dilation. So time dilation is the apparent difference in the time interval between two events as measured by two clocks. Albert Einstein concluded that the faster you move through space, the slower one moves through time. So this concept is best demonstrated through another thought experiment. Okay, so if you look at this, observer A is inside the spaceship. So there are two observers, A and B. Observer A is inside the spaceship that was in the previous slide, traveling at a constant speed through space, while observer B is on another slide, is at rest on Earth. So observer A has a light clock which is composed of a ball of light bouncing from a lower mirror to an upper mirror. So for observer A, the ball of light is moving vertically and the time it takes for the ball of light to come from the lower glass to the upper glass and then back to the lower glass can be referred to as 2 or the proper time. Okay. So, but from the perspective of observer B from the Earth, since the spaceship is moving at a constant velocity, the path traveled by the light is not vertical, but will have a horizontal component to it. So, the time interval for the ball of light to travel from the lower mirror to the upper mirror and back to the lower mirror from the perspective of observer B can be denoted or be at dilated time. Okay. So this is the observer B. This is from the Earth. Okay. Now we have the length contraction. Length contraction is the phenomenon in which an observer at rest would observe a moving object length to be shorter than its proper length. In everyday lives, length contraction, just like time dilation, is negligible. So for this concept, we will use another example. A ship is traveling from Earth to other planet. So we'll look at this event again at the perspective of observer A on the ship, and the perspective of observer B is on the Earth. So the distance between Earth and the planet is LO, which will be referred to as the proper length, as observed by observer B. So the observer B on Earth observes the ship moving at a constant velocity. So on the perspective of observer A and the ship, distance between Earth and the other planet will be different and will be denoted as L, which is the contracted length of the journey. So as observed by observer A, the relationship between L and LO is given by the equation. Okay, so L is equal to LO one is equal to velocity over C. So for example, the proper length of the distance between Earth and the planet is 10 light years as observed from Earth, and the ship is moving at a constant velocity of 80% speed of light or 0.8 speed of light. The contracted length or the distance from Earth to the planet as observed from the ship can be computed as 10 light years So this shows that the observer on Earth, the distance between Earth and the planet is 10 light years, but it would seem only 6 light years for the observer on the So we have now the mass energy equivalence. One of Albert Einstein's most famous equation, the mass energy equivalence, is the principle which concludes that anything that has a mass also has an equal amount of energy. So E is equal to mc squared, where E is energy, m is mass, and c is the speed of light. So since the value of c is very large, this equation implies that everything that has mass, even those at rest, have inherent energies, the kinetic energy, chemical energy, mechanical energy, and the nuclear energy, etc. in them. So these energies can be harnessed to do work, such as lighting a bulb, or to run an engine. So this equation also confirms that the speed of light is an absolute and ultimate speed because this speed can never be attained or surpassed by any massive object. So the mass energy equivalence, since the value of C is very large, this equation implies that everything that has mass, even those at rest, have inherent energy. So this equation, okay. Now we have the cosmic limit, speed limit. For centuries, scientists thought that speed has no limit. But Albert Einstein showed that in fact that there is a speed limit, and it is the speed of light in a vacuum. Based on his calculations, as an object travels faster, the more massive it needs to be, and as objects become more massive, more energy will be required for it to move faster. So therefore, it will take an infinite amount of energy for an object to reach the speed of light. Thank you, students, for joining me today in our online learning. So I hope you enjoy and, of course, learn new things in our lesson on the theory of relativity. So I know, class, that this is not easy for you at first, but as you go through with this, I know you will really understand. So I also posted here a link for you to look of for you to understand more. So I hope you will not fail to watch this on YouTube for better understanding. And class, I hope to be with you next week again. So see you next meeting, and God bless and stay safe, everyone.